All right, let's dive straight into this explainer and completely level up your embedded system skills. Today, we're totally transforming how you use the STM32 UART. We're going to take a really close look at one of the most fundamental peripherals inside microcontrollers, and honestly, we're going to push it to its absolute limits.
So here's our roadmap for today. We're starting off with the Universal Communication Standard. Then we'll talk about escaping the polling trap, followed by unleashing DMA. After that, we'll figure out handling unknown data lengths, and we'll wrap it all up with some true one-wire sorcery over UART. Okay, first up, Section 1, the Universal Communication Standard. Let's just quickly ground ourselves in the absolute hardware basics. Now, when you pull up the Connectivity tab for an STM32, you're usually going to see both UART and USART. So what's the actual difference here? Well, UART is strictly asynchronous. It relies entirely on timing that both sides agree on beforehand. USART, on the flip side, adds a synchronizing clock line. That extra line unlocks support for things like smart card communication and synchronous modes. But for our purposes today, we are focusing purely on the power of asynchronous communication. To communicate efficiently without that clock line, both the transmitter and the receiver absolutely must agree on the standard frame parameters. You know, a super common baseline setup is 115,200 baud rate, 8 data bits, no parity bit, and 1 stop bit. The crucial takeaway here is that if these parameters don't match exactly on both sides of your hardware connection, you're not getting data. You're just getting a screen completely full of garbage characters.
Right, let's move right along to Section 2, Escaping the Polling Trap.
This brings us to what is easily the biggest mistake developers make when sending data. When you use standard blocking mode, or polling, to send, say, a massive 10 kilobyte file, your CPU essentially just freezes. It completely delays everything else. Think of your CPU like an executive chef who's just standing there, completely frozen in place, staring at a microwave until it finally beeps. If your code is also supposed to be, blinking an onboard LED every 500 milliseconds, that blink rate is going to severely lag. Why? Because the CPU simply cannot execute the next instruction until every single byte of that file is sent out.
The elegant solution to this whole mess is interrupts. By switching from blocking mode over to interrupt mode, you're essentially handing your CPU a kitchen timer. Now, the CPU can go right back to chopping vegetables, or in our case, blinking that LED perfectly on time. It only jumps back over to the UART peripheral when the data transfer actually triggers a quick alert saying, "Hey, I'm done."
Which perfectly sets up Section 3, Unleashing Direct Memory Access.
So, interrupts are a massive upgrade for sure. But what if we have megabytes of data to move? A massive transfer like that still totally taxes the CPU because it has to wake up constantly for every single interrupt. So the really big question is, how do we completely free the CPU during a massive data transfer? We basically need an ultimate background worker so the CPU literally doesn't have to lift a single finger while data's moving.
Enter DMA, or Direct Memory Access. This is a dedicated hardware controller built right in. Going back to our restaurant analogy, think of the DMA as hiring a dedicated sous chef whose literally only job is to handle that microwave. The executive chef, your CPU, can now run the rest of the entire restaurant without breaking a sweat. This drops your CPU load to practically zero while data just flies out the serial port.
Now, when you're actually configuring DMA, you have a pretty important choice to make. Normal mode is basically a one-and-done operation. But circular mode, that brilliantly loops your buffers. Once the DMA hits the very end of the buffer, it just automatically reloads the addresses and starts right back at the top. It's absolutely perfect for handling stuff like continuous incoming audio streams or nonstop sensor data.
Moving into Section 4, Handling Unknown Data Lengths.
All right, here is where we hit a highly realistic, everyday bottleneck in embedded architecture. What if we simply don't know the size of the incoming data? When we configure the DMA, we usually have to tell it exactly how many bytes to expect up front. But setting a strict buffer size fails completely if an incoming file gets randomly chunked by the sender or just arrives at a totally unpredictable length.
Well, the solution is actually hidden right inside the STM32's hardware. It's called idle line detection. This is a super clever peripheral feature that detects when the receive line remains quiet for a set amount of time. It basically means the sender has paused. By pairing idle line detection with DMA in circular mode, the microcontroller automatically grabs the exact size of the received data the very moment the sender takes a breath. It completely bypasses the need to know the data length in advance. It's a total game changer.
Okay, get ready because we've officially reached the boss level of this explainer.
Section 5. One-wire sorcery over UART. We are going to utilize the UART's single-wire half-duplex mode to emulate a completely different communication protocol.
Consider the timing requirements for the extremely famous DS18B20 one-wire temperature sensor. A standard one-wire sensor doesn't have a clock line at all. Instead, it requires hyper-specific microsecond timing constraints just to register zeros and ones. To write a bit 0, you have to pull the line low for exactly 60 to 120 microseconds. To write a bit 1, you pull it low for just a tiny fraction of time, and you absolutely must release it within 15 microseconds.
So here is our puzzle, and it's a good one. How on earth do we emulate these incredibly precise, highly specific one-wire timing signals using a standard kind of chunky UART data frame?
Well, check this out. If we set the UART to 115200 baud, a full 9-bit frame takes about 78 microseconds. That perfectly fits the timing to write a 0 if we just send the byte hex 00, which pulls the line low the entire time. Or we can write a 1 by sending the byte hex FF, which only pulls the line low for a fraction of a microsecond. It's brilliant, but there is a massive catch. Waking up the sensor in the first place requires a strictly mandated 480 microsecond low reset pulse. And honestly, that is physically impossible at our normal 115200 UART speed.
Which leads us to what I think is the ultimate embedded hack. First, we temporarily drop the UART baud rate way down to 9600. At this incredibly slow speed, sending the byte hex F0 stretches out the low bits into a massive 520 microsecond reset pulse. This completely fools the sensor. Then, the instant presence is detected, we snap the baud rate right back up to 115200 to issue the skip-rom commands, reading all the incoming data via DMA seamlessly in the background.
And the result of all this sorcery? By using this DMA-backed half-duplex UART magic, the CPU doesn't have to manage a single microsecond of blocking delay. It literally just effortlessly processes the one-wire timing, reads the 2 bytes of data, mathematically shifts them together, and accurately tracks a real-world cup of cold water dipping to exactly 1 degree Celsius in real time. It's just so cool to see it work.
Mastering the underlying hardware like this just opens up endless creative possibilities. Think about it. We took a peripheral meant for basic serial text, strapped a DMA controller to it, weaponized its idle line detection, and then warped its baud rate on the fly just to speak a completely foreign sensor language. It really leaves us with one pretty big question. What hidden protocols will you hack together next?